Okay, so far we have discussed about first order differential equations, and now we will discuss about second order differential equations, and we will discuss about only the linear differential equations. So we know that the general expression of the nth order linear differential equation uh, is this shown in the equation 1. Yeah, equation 1. Now, so here this it is a linear differential equation because the coefficient of y and all its derivatives are a function of x. So here a0, which is the coefficient of y, is a function of x, and a1, which is the coefficient of dy dx, is also a function of x, and all other a are function of x. And also the power of y and all its derivatives are 1. So is 1. So see here that the power of y is also 1, the power of dy dx is also 1. So it is the linear differential equation. Now from this general expression of the nth order differential equation, we can obtain the expression for second order linear differential equation. So for second order linear differential equation, the expression would be this. So so this is a2 d2y dx2 plus a1 dy dx plus a0 y equal to gx. So it will contain the derivatives up to second order. So it contains on what contains the second order derivative of y, first order derivative of y, and y itself. Now dividing this equation by a2x, so we get d2y dx2 plus a1 by a2 dy dx plus a0 by a2 y equal to g of x by a2 of x. Now here this ratio a1 by a2 is written as px. P, which is another quantity, is a function of x, that is the coefficient of dy dx, and a0 by a2 is written as q of x, which is another quantity and is a function of x, into y equal to r of x. So it is written as y double dash plus p of x y dash plus q of x y equal to r of x. So here double dash means that this is the second order derivative, the double derivative of y, and y dash means there is the first order derivative of y, that is the uh, single derivative of y. And so equation 2 we have obtained this is the general expression for a linear second order differential equation. Now suppose the initial value problem of a second order linear differential equation is this. So this is the second order differential equation, equation 2, when subjected to the initial conditions, that is y at x0 is equal to y0 and y dash at x0 is equal to y dash 0. So here y at x0 means that is the value of y at x equal to x0. So the point is x0 y0, and y dash is the derivative of y, and y dash of x0 means that is the derivative of the y at x equal to x0, which is equal to y dash 0. Now we will discuss about the existence of a unique solution. uh, we already know that the condition, that is the criteria for the existence of a unique solution, that is a function that is the right hand side of a of the first order differential equation, which is the function of x, has to be continuous, and the partial derivative of the function with respect to y should be continuous. So in this case, that is for second order differential equation, also we have to calculate the unique solution for a second order linear differential equation, because the second order differential equation can have more than one solutions. We will discuss several examples about it. Now let us discuss about the existence of a unique solution. So it is written here, suppose p of x, q of x, and rx. So you know that the p which is the coefficient of y x, and q which is the function of y, and r which is the right hand side part. So if these three functions are continuous function, if these are continuous functions on a closed interval ab, so the closed interval ab means that is these three functions are continuous for all values of x between a and b, including the end points, that is the a and b. That is why it is called closed interval. Now if x0 is any point uh, in AB, and if y0 and y dash are any numbers, whatever maybe, then equation 2, so this is the equation 2, has one and only solution, y of x on AB, such that y at x0 is equal to y0 and y dash of x0 is equal to y dash 0. So let me repeat that if PQR are continuous functions on a closed interval AB, and if x0 is any point, and if y0 and y dash are any numbers, then y of x be the unique solution of the second order differential equation on that interval AB, such that this condition is satisfied. So it means that the unique solution of this differential equation would be y of x on that interval, and if p, q are continuous functions of x on that interval, and it passes through the point x0 y0 with a slope that is y dash 0. So the initial the solution of the differential equation to that is the y of x uh, will pass through this point x0 and y0. The solution of the differential equation, this would pass through this point x0 y0 with a slope y0 dash. If this condition, that is p, q, r are a continuous functions of x on the interval ab, on the interval ab, closed interval a of b. So let us discuss about an example. Suppose this is the initial value problem. Here y double dash plus y equal to 0 is the second order differential equation. It is a linear differential equation, and we can say this is a differential equation with constant coefficients. So here the coefficient of y is a constant one, and coefficient of y double dash is a uh, constant one. Now this differential equation has two solutions, either y equal to sine of x or y equal to cos of x. For both these solutions, this differential equation is satisfied, because uh, if we calculate y dash and adding with y, we can obtain 0. So if y equal to sine of x, so then y dash equal to cos of x, and y double dash equal to minus sine x. So y double dash plus y is equal to 0. Similarly, y equal to cos of x is also a solution. So here y dash equal to minus sine x, and y double dash equal to minus cos x. So y double dash plus y is also 0. So for both the solution, so both these functions y equal to sin of x and y equal to cos of x, this differential equation is satisfied. So these are the two solutions of this differential equation. Now from these two solution, we have to find out which is the unique solution of this differential equation. The nature of these two functions are different, and so it will depend on the initial conditions. That is, when suppose the initial value problem is this differential equation when y of 0 equal to 0, that is the origin 0 0, and the slope at origin, that is y dash at x equal to 0, is equal to 1. So we have to check that which solution is satisfying these initial conditions. So if y equal to sin x is the solution, y equal to sin of x, then y dash equal to cos of x. So from this equation, you see that y equal to 0 at x equal to 0. So putting x equal to 0, we get y equal to 0. So this condition is satisfied. Now from this equation, you see that uh, mm, if you put x equal to 0, then we get y dash equal to 1. So this condition also satisfied. So we can say that y equal to sin of x is the unique solution of this differential equation. And here p, q are these are continuous or not, uh, doesn't need it, because the coefficient of y and y double dash are uh, 1, and this is simply constant. So so we don't have to check that if p, q are continuous or not. So so the unique solution of this differential equation is y equal to sin of x, because for this function these two initial conditions are satisfied. Now let us discuss another example, that is y double dash plus y equal to 0 when y of 0 equal to 1 and y dash of 0 equal to 0. So for this initial value problem, you see that y equal to cos of x will be the unique solution. For this differential equation, y double dash plus y equal to 0, y equal to sin of x is also possible, and y equal to cos x is also possible. But for this differential equation and with these initial conditions, y equal to cos x will be the unique solution, because uh, so here y equal to cos x, if we take x equal to 0, then x equal to 0, then y equal to 1, and here y dash equal to minus sin x. So here if x equal to 0, then it becomes y dash equal to 0. So y equal to for this function, this initial condition is satisfied. So for this initial value problem, the unique solution of this differential equation is y equal to cos x. So first example, that is y double dash plus y equal to 0 with y of 0 equal to 0 and y dash 0 equal to 1. You see that the unique solution is y equal to sin x, and it passes through the origin. So you see here that it passes through the origin 0 0. That is why y equal to sin x is the unique solution of this initial value problem. But for this differential equation or this initial value problem, y equal to cos of x will be the unique solution, because it passed through this point 1 0. Because for this because for this differential equation, the solution would be this. So this is the plot of y equal to cos x. So the so for cos x, it starts from 1 0, 0 comma 1. So it satisfies the initial condition, that is x equal to 0, y equal to 1, 0 1. So y equal to cos x is the unique solution of this differential equation. Now next we will discuss about homogeneous and non-homogeneous differential equation. The equation 3, that is y double dash plus p of x y dash plus q of x y equal to r of x, is a non-homogeneous differential equation. And from this non-homogeneous differential equation, we have obtained the homogeneous differential equation is y double dash plus p of x y dash plus q of x y equal to 0. So for homogeneous differential equation, you see that the right hand side term r of x is equal to 0. So this is the homogeneous differential equation associated with this non-homogeneous differential equation. Suppose this is the equation 3, non-homogeneous differential equation, and this is the equation 4, that is the homogeneous differential equation. Now this homogeneous second order differential equation is different from the first order homogeneous differential equation. So for second order, this is it is homogeneous when only the right hand side term, that is r of x equal to 0. Now let us discuss about the solution of a non-homogeneous differential equation. We know that the general expression or general expression of the first order linear differential equation is of the form that is y, that is which is the solution is the general solution is basically is a function of x and c, or the general expression can be written as g of x y comma c equal to 0. So the solution is of the form that is g of x y c equal to 0 for a first order linear differential equation or nonlinear. Some suppose like y equal to c into e to the power x square. So the general solution is a function of x and c, that is the independent variables x and one constant c, and the solution is of the form g of x independent variable y comma c equal to 0. But for second order differential equation, we have two constants. That is why the general expression for the non-homogeneous differential equation would have two constants, that is c1 c2. So the so we are discussing about the solution of a non-homogeneous differential equation. If y of x is any solution, so you have seen already that the second order linear differential equation has uh, uh, more than one solutions. And so if y of x is any solution, suppose it is any solution of the non-homogeneous differential equation, and it can be written as y of x equal to yg of x comma c1 c2 plus yp of x. So here this yg, this is the general solution of the homogeneous differential equation, this equation 4. So yg is the general solution of this homogeneous differential equation, and this yp is the any particular solution of the non-homogeneous differential equation 3. So let me repeat again that if y of x is any solution of the non-homogeneous differential equation, then y of x can be written as, that is, it is a combination of the yg plus and yp, where yg is the general solution of this homogeneous differential equation and yp is any particular solution of this non-homogeneous differential equation. Sometimes this solution y of x is said to be a complete solution of the non-homogeneous differential equation 3, complete solution. So which is yg, and which is yg plus yp. So now we'll prove that this y of x is the complete solution of the non-homogeneous differential equation. So so here that is the proof that uh, yg of x c1 c2 equal to y of x minus yp of x. So from this equation for we can write that yg of x comma c1 c2 equal to y of x minus yp of x. We will prove this equation 4, that is the complete solution is equal to the general solution of the homogeneous differential equation and plus ypx, that is the any particular solution of the non-homogeneous differential equation. So if we prove that that y minus yp is the general solution of the homogeneous differential equation, so that we can write the yg is equal to y of x minus yp of x. So so we have to prove that this y of x minus yp of x is the general solution of this homogeneous differential equation. So we have to prove this line. So because y and yp is any solution of the non-homogeneous differential equation, so from the homogeneous differential equation we write that suppose let me first write the homogeneous differential equation y double dash plus p of x to y dash plus p of x to y equal to 0. So this is the homogeneous differential equation associated with the non-homogeneous differential equation, which is y double dash plus p of x y dash plus q of x y equal to r of x. Here by this y minus yp of double dash plus p of x y minus yp dash plus q of x to y minus yp of dash, that is y double dash plus p of x into y dash plus q of x into y. So now writing this in a separate term and minus, we can write as yp of double dash plus p of x to yp. This is p in Sanskrit level, yp dash plus q of x into yp dash equal to 0. So so you can see that y double dash plus p of x, so y dash plus q of x into y. So here y is a solution of the non-homogeneous differential equation. So this is equal to r of x and minus, and yp is also any particular solution of the differential equation which is also r of x, then we can say this is equal to 0. So that is so we can write, so we can say that for this solution also the homogeneous differential equation is satisfied. So we can say that y of x minus yp of x is the general solution of this homogeneous differential equation. And we know that that is yg is the general solution of this differential equation, then yg is equal to y of x minus ypx. So from this equation, so we can write that y of x equal to yg plus yp. So the part we can say that any solution of this non-homogeneous differential equation uh, can be written as a sum of yg plus yp, which is called the complete solution of this non-homogeneous differential equation, where yg is the general solution of the associated homogeneous differential equation, and yp is any particular solution of this non-homogeneous differential equation. Hmm. Now, from the homogeneous differential equation, you see that the homogeneous differential equation y double dash uh, of x plus p of x. Now, suppose skip this part. The homogeneous differential equation y double dash plus p of x into y dash plus q of x y equal to 0. You see that this in this homogeneous differential equation, um, if you take that y equal to 0, then all then for this value all this differential equation is also satisfied, because y equal to 0, then this is also, this term is 0, this term is also 0, and y double h is also 0. So for y equal to 0, the homogeneous differential equation is also satisfied. So we can say that y equal to 0 is always the it is the uh, trivial solution of the homogeneous differential equation. So y equal to 0 is said to be the trivial solution every time, trivial solution of a homogeneous differential equation. So homogeneous, either linear or non-linear, that doesn't matter, because y equal to 0, if y equal to 0, then y dash, y double dash, both are 0. So so for any homogeneous differential equation, either linear, non-linear, the y equal to 0 is the trivial solution, which is fixed. Now suppose y of x is any solution of this homogeneous differential equation, then we can prove that that c into y of x, where c is a constant, c of y is also a solution of this homogeneous differential equation. So if y of x is any solution, then the any constant multiplied by that solution is also a solution of this homogeneous differential equation. So we can prove that. Suppose now the solution is c into y, so c into y plus p of x, that is c of y, this is dash, q of x equal to c into y. So c into y. So we have to calculate this term. Let me check which is either 0 or not. So it is simply that c into y double dash plus p of x into y dash plus q of x into y. So this is equal to 0, because this is 0, then c into 0 is equal to 0. So c into y of x is also a solution. Now let me check if this type of solution, this type of function, suppose c1 y1 of x plus c2 y2 of x is a solution of the homogeneous differential equation or not, where y1 and y2 are any two solutions of this homogeneous differential equation. Suppose suppose y1 and y2 are any two solutions of the homogeneous differential equation. So then we have to prove that then c1 y1 plus c2 y2 is also a solution of this homogeneous differential equation. So if this is solution, then for this solution this differential equation will be satisfied. So we have to replace y with this term. So from this equation, that is the left hand side, we can write c1 y1 plus c2 y2, that is double derivative, and plus p of x into c1 y1 plus c2 y2 dash plus q of x into c1 y1 plus c2 y2. So now and we can write c1 into y1 double dash plus p of x into y1 dash plus q of x into y1 now plus c2, this is y2 double dash plus p of x into y2 dash plus q of x into y2. So there is c1 equal to 0, this is 0, and plus c2 into 0. So this is 0, which is right hand side. So we can say that so we can say that this term, this function is also a solution of this homogeneous differential equation. So here this function is is said to be a linear combination of y1 and y2. So if y1 and y1 and y2 are any two solutions of this homogeneous differential equation, then their linear combination is also a solution of this homogeneous differential equation. So in terms of theorem, we can write that. So I can write if y1 and y2 are any two solutions of the homogeneous differential equation, if y1 and y2 are any two solutions of the homogeneous differential equation, then the linear combination of y and y2, which is c1 y1 plus c2 y2. Here y1 and y2 are both function of x. So if y1 and y2 are any two solutions of the homogeneous differential equation, then the linear combination of y and y2, which is c1 y1 plus c2 y2, is also a solution. Is also a solution of the homogeneous differential equation. Okay. Now we will discuss about that is linear dependent and linearly independent functions. Now uh, suppose if any solution, suppose y1 or y2, if uh, if if any solution is written as a constant multiple of another solution, then these two solutions are said to be a linearly dependent. Otherwise they are called linearly independent. Suppose suppose this y2 is written as y2 equal to c into y1, or y1 equal to c into y2. So you see that the solution y2 is written as a constant multiple of the solution y1, or y1 is written as a constant multiple of the solution y2. So then these two solutions y1 and y2 are said to be linearly dependent. Linearly dependent. Linearly dependent means there is one solution varies linearly with the other solution, another solution. That is why they are called linearly dependent on each other. So the so we can say, suppose this solution, we can write y2 equal y2, so y2 varies linearly with y1. So if this now if the solutions, if any solution varies linearly with the another solution, then these solutions are said to be linearly dependent. Otherwise they are called linearly independent. If it is not written in this form, then y and y2 are called linearly independent. Now so we will discuss about a theorem that is mm, it is, so let me write that let y1 of x and y2 x let y1 and y2 be linearly independent solutions. Linearly independent uh, solutions of the homogeneous differential equation, which is y double dash plus p of x into y dash plus q of x into y equal to 0. Uh, so, let us consider that y1 and y2 be linear independent solutions of the homogeneous differential equation y double dash plus p of x into y dash plus q of x into y equal to 0 on the interval on the interval interval, suppose the closed interval, then then c1 y1 of x plus c2 y2 of x is the general solution uh, of this differential equation on the closed interval a b. So we can so this is a theorem, that is, if y1 and y2, if y1 and y2 be linearly independent solutions of a homogeneous differential equation, which is y double dash plus p of x into y dash plus q of x into y equal to 0 on the interval ab, then c1 y1 of x plus c2 y2 of x is the general solution of this differential equation on that interval ab. So on this interval ab, so any type of general expression uh, so any type of any type of solution can be obtained by suitable values of c1 and c2. So any type of solution, sorry, so this is the general solution. So for any values of c1 c2, that is suitable values of c1 c2, we can obtain any solution of this homogeneous differential equation if y1 and y2 are linearly independent solutions. That means y2 will not vary linearly with y1 or vice versa. Now we have to find out the criteria or the condition for which these two solutions y1 and y2 are linearly independent of each other. Okay, now we will discuss about the criteria for a linearly independent solutions. Suppose y of x be any solution of the homogeneous differential equation. Suppose suppose y of x be any solution of that homogeneous differential equation y double dash plus p of x into y dash plus q of x into y equal to 0 on an interval closed interval a comma b. So so if y of x is any solution of this homogeneous differential equation on a closed interval ab, then we can find the values of c1 and c2 such that y of x can be written as y of x is equal to c1 y1 of x plus c2 y2 of x and for all values of x on the interval a comma b. So if y of x is any solution of this homogeneous differential equation, and if y1 and y2 be any independent solution of this suppose we consider that y1 and y2 are independent solutions, then we can say that y of x is equal to c1 y1 plus c2 y2 be the solution if for a suitable value of c1 and c2 for all values of x on that interval ab. We can consider this is the solution. So and now we consider this suppose we consider this is the unique solution, then it will pass through a point x0 with a a specified slope such as y dash 0. So where y0 is equal to y of x0 and y dash 0 is equal to y dash of x0. So we can write that so we can write that for these values we can calculate that the C1 and C2. So that is, we can write this expression for these two values. So so at x0, C1 y1 at x equal to x0 plus C2 into y2 at x equal to x0 is equal to y0. There is y at x0. So calculating y of x at x equal to x0, so which is C1 y1 of x0 plus C2 y2 of x0, that is equal to y0. Similarly, for the derivative, we can write that is C1 y dash 1 of x0 plus C2 y2 dash of x0. Suppose the derivative exists. Suppose the derivative of the independent solutions are exists, then so this C1 y1 dash x0 plus C2 y2 dash x0 is equal to y dash 0. So y dash 0, which is equal to y dash of x0. Now we can find the value of C1 and C2 by solving these two solutions, and if we follow the Cramer's rule, then the value of C1 and C2 can be found only when the determinant, which suppose the determinant is represented by a quantity which is called the W. The determinant is y1 of x0 and y2 of x0, and here that is the derivative of y1 dash of x0 and then y2 dash of x0, so which is not equal to 0. So let me repeat again that so if y of x is any solution of the homogeneous differential equation on that interval AB, and if y1 and y2 are the independent solutions, then we can find suitable values of C1 and C2 such that we can write y of x is equal to C1 y1 plus C2 y2. Now to find out C1 and C2, we have to put the initial conditions on that solution, and if we apply the Cramer's rule, then this determinant should not be 0 to find out, to calculate the values of C1 and C2. So so C1 and C2 can be determined only when this determinant, that is the coefficient of this in this equation, that the C1 and C2, that is y1 y2 and y1 dash and y2 dash. If this determinant is not equal to 0, then only we can determine the value of C1 and C2. So the expression of this so the value of this determinant, so which is represented by a quantity that is W, which is called the Wronskian. So which is written as W, so W, which is the Wronskian. So this is written as the Wronskian. So W of function of y1 and y2, two independent solution, is equal to y1 y2 dash minus y2 y dash, and this is the Wronskian. So for so to determine C1 C2, so this W cannot be 0. Now Now here you see that this w or this determinant is determinants is calculated or in terms of in with respect to that point, that is x0. So with respect to x0, this calculations are done with respect to x0. Now we can prove that if that this point has no importance, uh, uh, because 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 if this w is either identically 0 or not 0 on that interval wb. So what I said that we can see that this value w is either identically 0, that is w is either identically 0 or not 0 for a solutions to be linearly dependent or independent. We will see that. Now now the identically 0 of this it means that there is making w equal to 0 identically. W that is the Wronskian is identically 0 means that making w equal to 0 for all values of x. So making w equal to 0 for all values of x. Now see, suppose this function p, a and q are continuous on the interval ab. So and if y of x is the solution, so if y is unique, then if y of x is unique, then then it will pass through that point x0 y0 with a specified slope y0 dash. So these initial conditions are fixed. So if these initial conditions are fixed, then from these initial conditions, then we can find calculate the c1 and c2. So and from this we can calculate the unique solution yx. Now if now it is p and q are continuous function, we consider that p of x and q of x are continuous functions on the interval ab, and we also consider that y of x is uh, unique. So so that c1, so the value of c1 and c2 can be determined uniquely. So so if c1 and c2 is determined uniquely, then w must be not equal to 0, because y of x is a unique solution. Then w is not equal to 0. So this is fixed. If c1 and c2 is determined uniquely, then w cannot be 0. So for now, so for unique solution, we can say that w equal to w not equal to 0 for unique solution. So let me repeat again that for unique solution, we can determine c1 and c2 in uniquely, and so if c1 and c2 determine uniquely, then w cannot be 0. So w is not. Now making w equal to 0, so that is w equal to 0, making w, that is w is identically 0 for that is identically 0 means for all values of x on AB. That is on that interval for any values of x equal to 1 2 3, any values of x, making w equal to 0 strictly. So if w equal to 0, then this term is also equal to 0, that is y1 y2 dash minus y2 y1 dash is equal to 0. Now dividing by y1 square, so y1 y2 dash minus y2 y1 dash by dividing by y1 square equal to 0. So this term, that is the left hand side term, can be written as d of y2 by y1 equal to 0. So y1 fixed y1 square, okay. So y1 fixed y2 dash minus y2 fixed y1 dash. So this can be written as d of y2 by y1. So from this we can write that is y2 by y1 equal to constant. Suppose this is the c, and so we are calculating for all values of x. So for all values of x we can write that is y2 of x equal to c1 into y1 of x. So when w is identically 0, that is for all values of x making w equal to 0, then from this we find out that y2 of x is equal to c into y1 of x. So which we discussed earlier, that if any solution is written as a constant multiple of the another solution, then they are said to be linearly dependent. So here y2 varies linearly with y1. So if w is identically 0, then these two solutions y1 and y2 are not linearly independent, they are linearly dependent. So if w equal to 0, then y1 and y2 are linearly dependent, and if w is not equal to 0, then we can say y1 and y2 are linearly independent. So this is the criteria, and which we are proving that what is the condition for y1 and y2 to be linearly independent. If y1 and y2 are independent solutions, we are talking about the independent solution. So if y1 and y2 are independent solution, then this complete solution, that is the general solution, that is c1 plus c2 will be unique solution, and then that means c1 and c2 can be determined uniquely, that is c1 c2 uniquely determined. That means w not equal to 0. So these two conditions are satisfied simultaneously. So if y1 and y2 are independent solution, then c1 and c2 can be determined uniquely, and so that w is not equal to 0. So in this way they are linked to each other. Now let us discuss about an example. Suppose example, suppose y double dash plus y equal to 0 subjected to the initial condition, that is y of 0 equal to 2 and y of 0 equal to 3. Let me check that is that is the y equal to c1 sine of x plus c2 cos x is a general solution of that differential equation or not. So we know that y equal to c1 y1 and c2 y2 are the is the general solution of the homogeneous differential equation, and if and we consider that y1 and y2 are the two independent solutions, any two independent solutions of the differential equation, then we can write the solutions y1 equal to sine of x and y2 is equal to cos x. So so you see that the initial conditions are given: y of 0 is equal to 2 and y of 0 equal to 3. So from this equation we can determine the unique solution y, and we can find out the values of c1, c2. So w will be not equal to 0. So let me check that. So the w, which is the Wronskian, is, that is y1, y2 and y1 dash and y2 dash. So y1 here, this is the sine of x and this is cos x, and y1 dash is cos of x and y2 dash is minus sine x. So it is simply equal to minus sine square x and minus cos square x is equal to, so w is not equal to 0. So we can determine c1 and c2 uniquely. That means the two solutions y1 and 2 are linearly independent of each other. Then we can say that y equal to c1 sin x plus c2 cos x is a general solution of that differential equation y double dash plus y equal to 0, subjected to these initial conditions.